Hello, everyone. So it's my pleasure to tell you about our work at the University of Applied Sciences, Northwestern Switzerland, and the spin-off MatterDecoder on how we are getting towards quantum utility for nuclear magnetic resonance simulations on NISQ computers. So about quantum utility, as taken from a concept from Scott Aronson, is that today we are looking at NISQ projects, meaning that they can run on NISQ architecture, meaning that there is activities that make it running. So in terms of hardware algorithms, it should be also efficiently verifiable, so that we can actually verify the utility, and it should have, in principle, quantum advantage in nature. And in fact, it turns out that simulating nature problem like NMR, as I will mention, qualify for all of these three categories. And so NMR, which stands for nuclear magnetic resonance, is a very powerful tool used for decades already, with a strong legacy of many Nobels also that made decades the technique more and more useful, and in particular in providing atomic level information of molecules, be it structure, interaction, dynamics. And it can be in liquid form, very, very useful for things close to our biology in our body, or solid state form as well. And one of the issues is that getting out of the spectrometers, we get spectra, but then to go from the spectra to the useful molecular information is actually a hard problem, and today still requires experts and human intervention to actually do analytics. And for some specific molecules, it can take up to a few months or even PhD studies to actually take out all of this information. And the reason is that getting from spectra, so this is now a 2D spectra and a full range of different type of spectra, it's a ill-pose inverse problem to get back to the structure. And so, in fact, getting from the spectroscopic data to the molecular structure is a hard problem. But the good thing is that to get from a molecule to such a spectra, there is a theory that describes it pretty well, which is fully quantum. Though the issue, if we want to simulate it classically, is that it falls into an exponential wall, as I will explain. Every time we add one more spin that is NMR active, we increase exponentially the complexity of the problem. So now we are then interested in simulating this spin dynamics, so nuclear spin, so meaning really the nuclear spins in a molecule, to get this efficiently. And so in a nutshell, for those not familiar with nuclear spin dynamics, if we look at the molecule here, we see blue hydrogen atoms. There are these spin interactions between them. And so in practice, spins as this little magnets picture, they interact with magnetic fields. And second, they can also interact with one another, like on this water molecule. And second, so these are the two terms of the Hamiltonian we are interested in simulating. And second, the spins are shielded from the electronic clouds around them, and which is why the unique electronic structure in a molecule serves as a fingerprint for molecules. This is why this technique, by looking at nuclear spins, allows to get this specific molecular fingerprint of the molecule. So now, to describe more mathematically the spin interaction, we can have a spin matrix, coupling matrix, where we have the coupling terms here in red that would describe the interactions, which we could map to some kind of graph to see how connected such spin system can be. And this example, even for a small molecule, we see that can be already quite connected, and we see the more we go to the diagonal term, the deeper the coupling is, and the more strong the coefficients are, the stronger the coupling is. And so this coupling regime and depth of coupling is definitely very important in knowing if it's classically tractable or intractable, and when quantum computing comes at hand. And as an example, if I take a slightly bigger molecule like ATP, I will come back to this later, we see, for instance, that the couplings, it's less coupled, and in fact, we even have this cluster, and here 2 little clusters of spins that are not coupled. And in fact, when we can cluster a molecule, and especially when we have weakly coupled systems, we can compute it classically. And this in fact has been already used for 15 to 20 years to be able to even simulate very large proteins in cutting it down in small clusters of, let's say, 5 spins. Though for more highly correlated systems, it has proven to be inaccurate. So for instance, these hard classical simulations are for large clusters where we cannot cut it into small clusters, or for strong coupling where the coefficients, where the strong coupling cannot be considered into a weak coupling to decompose the system, or when we have weak fields or even zero field NMR, and so on and so on. So if we look at the increasing spin system for increasing molecule size, when we go around 20 spins, we hit this exponential wall where we cannot simulate the full molecule, and especially for molecules where computing the full system is necessary for getting a specific information. And just to show an example for low field is, if we look at high fields where we can do some kind of approximation, we can basically get a spectrum by some kind of linear combination of first principle physics. But as we go to low field, you see that it's more difficult to interpret the spectrum. And even this is from a very simple molecule, just a toy model, just to show that even when we enter in some specific regime, the spectra become much more complex to analyze if you were to do the backward, the inverse problem. So now, let's go from this semi-classical treatment to full quantum mechanical treatment. And in fact, this spin simulation is a perfect quantum native problem, and it goes back to this original idea of quantum computing of Richard Feynman, that these molecules are actually described fully quantum mechanically. And in fact, up to now, most of the simulations has been quantum mechanical on classical computers, where from the start we do a bunch of approximations so that the simulations can run. But now with the opportunity to run fully a quantum model on a quantum processor without making approximations that will make it less accurate. And so we can then map directly this NMR system to a spin system that we can map directly to a QPU. And what is interesting is that compared to electronic system where we have to do the mapping from fermions to spins, where there is a huge overhead in terms of gates, and we already lose the advantage. Since we do nuclear spin, we don't have this issue. We can assign one spin to one qubit, so the mapping is 1-to-1. We don't have this huge overhead. So when some electronic simulations that are super interesting and useful for quantum application in chemistry, we don't suffer from this large overhead. So it means we can already work on significantly large spin systems with the current NISQ hardware. And so we are interested in simulating this Hamiltonian, and our goal is to do the Hamiltonian dynamic simulation. So basically solving this. And if we look for our Hamiltonian, the scaling is pretty bad. If we are to do the classical diagonalization, because it scales as 2 to the power n to 2 to the power n. But in fact, the circuits that gets from it, this we can store, which is why it's a native quantum problem where the scaling can actually be favorable. And so if we look at an example, we did a few examples, and here we pick ATP, adenosine triphosphate, because it is found in all known forms of life. It's involved in some energy transfer processes. And so it means already with 8 active spins from the NMR perspective, so proton NMR, we can already do a simulation on a molecule that at least is relevant and found in biological processes. And you see that for 8 spins, we can already be on molecules with a large number of atoms, because here we only have a few hydrogen atoms that are useful in terms of NMR. So now if we look, actually I just realized this is not ATP for this figure, but everything that I'm going to say applies, is that the mapping, as I mentioned, is one-to-one from a spin system to a qubit. We have the single gate operations, in particular for the non-coupling terms, so direct field interaction as an example, and then we have sets of 2 qubit gates for the spin-spin interactions. And in this transpiled circuit, we only work on pure states. So if we were to integrate statistical effects closer to some NMR experiment, we could use also treatments with density matrix, but it doesn't change for the generality of the treatment here. And we just have a simple initialization where we flip the spin like with a pi pulse on the XY plane, and then we are good to operate. And so the simulations here were carried out on the Eagle R3 architecture from IBM, and this was actually made possible by Quantum Basel. Quantum Basel is a hub for AI and quantum technology based out of Basel, and they provide technology access and support to various processors like IBM, IonQ. And here, in fact, key parameters, so the number of qubits, 127, and here when we talk about 10, 15 qubits, spins, sorry, we talk about 15 qubits. So in fact, we underuse the number of qubits. However, what is very interesting is the number of gates that we can use, so the depth of the circuit that can be run on this hardware. And so shifting to the results, so this Hamiltonian dynamics, we measure at the end the magnetization, like in an NMR experiment, and this is called the free induction decay. And so this is how the spin decay over time after this pulse excitation. This is an example of the FID for ATP. And then we can look at the spectrum and compare it to real NMR spectra that we did in the lab with an actual NMR experiment. And it's actually pretty interesting and matching. And of course, there are still noise issues and normalization, but at least for the main coupling terms, we have them. And if we look here, an example of a smaller spin system, it's also similar. We can even observe the triplet structure in this case for some of the couplings. This is very positive in terms of being able to run these simulations on a QPU. And to our knowledge, this is also the first simulation carried out for high field NMR on QPUs. Now, in terms of the Hamiltonian simulation, we looked a bit at the product formula to be used. And in fact, if we look at the literature, what we use currently is only one repetition. The thing is that if you look at the cosine distance compared to a perfect simulation with direct exponentiation, we see that we could maybe get better as we go to more repetition. But if we do this on the current hardware, we would have much more gates and then fall into the noise regime. So all the work that we present here were made with one repetition. Though for the future, there are very interesting results from companies like HiQ, where potentially you can increase this number of repetition and then get into a better accuracy regime. And this is also done with another product formula, NMR, for just a comparison purpose. Now, if we look at the main outcome in terms of resource estimation, we looked at the number of gates as we increase the number of spins. So what I show first in gray here, this is with this axis, which is a classical computation time, which is in seconds. And when we do it for a number of spins here, up to about 10 spins, this is where it starts already to break down, where we cannot run it with some of the classical simulators. And I remind here, this is a log scale. So this is actually an exponential curve. So this is our exponential wall. But now, if we do look at the ECR depths and the gate count, what we see is that we have this very beautiful polynomial scaling. And if we look at the actual numbers for what some of the transpiled circuits here up to a couple of tens of spins, we see that we fall in a range of a couple hundred gates. And if we want to go below this exponential wall, let's say at 20, 25, we only fall in about thousands of gates. So it means that we can get into a range accessible with current NISQ hardware, where we can work on bigger, fully connected spin systems that are not tractable with classical simulations. And if we look in terms of spins, in a molecule, not all spins are NMR active. And so if we look at the size of the molecules that could be addressed, we are talking about much bigger molecules. So meaning, for instance, already around 20 spins or 25 spins, we are talking about 50 to 60 atoms, so already large relevant molecules. And in terms of applicability, in this range, we already fall into categories of relevant molecules for industry, like catalysts, batteries, new materials, small drugs. And so this is for us a way to this NISQ quantum utility through this NMR analysis. And if we match to some of the quantum roadmap, this is last updated from IBM, we see that in terms of time scale for the resources available, we are also very much well aligned with the number of gates and qubits that could be leveraged to work on bigger and bigger spin systems. Now, if we put this more into perspective in terms of usability for end users, chemists who would not care if we use quantum computing or any other algorithm, if we want to really work on the inverse problem, which is to go from a spectrum to molecular information, in fact, it would be integrated in hybrid algorithms where we would use the speed and power of classical computing to make first guesses, and then quantum computing to actually get the accuracy and to get to the actual structure, and in an iterative process to actually end up on the molecular information. And ultimately, the goal is to help automate NMR and to help decipher spectroscopic data. So getting, for instance, on a powder, which can be for catalysts or it can be for drugs, in the pharma industry with increasing regulations requirements, where solid state is very hard to compute classically. But then with this pipeline, with outsourcing some of the spin calculations, the hard ones on the quantum computer, we could get to this useful molecular information. And then, in fact, more generally, this could be used for other spin systems, like in sensing NV centers. We've heard a lot, for instance, about it today, and also many more applications like in solid state, material development, etc. And this technology is being made available through the spin-off MatterDecoder, which is also currently in the Creative Destruction Lab Quantum Stream Accelerator. And so if you're interested also to contribute to this, please reach out, join us. And this work is the work of Artemi Burov in particular, and also was made possible by our sponsor, in particular, Quantum Basel. And with this, thank you again, and happy to answer your questions.
Any questions from the floor?
Is it agnostic to the type of quantum computer, or are there preferences for which architectures are better, perhaps in terms of noise?
Yeah, a priori it is agnostic, but of course we would go to the best architecture in terms of noise and connectivity. Yeah, that could be leveraged for this type of project. Calculations. Yeah.